Alright kiddos, welcome back. We're going to review for the solutions portion of our next exam now. As you might recall, there was a boatload of vocabulary related to solutions. I'm not going to go over every term with you at this point. Please go through those terms on pages 116 to 118 of your manual. Simple terms like solute, solvent, solution. Remember what a colloid is, and along with that, I would look at what a Tyndall effect is. Know what a suspension is, and know how that's different than a colloid. Be familiar with the term alloy. Aerosol, we had that on one of our assignment questions, didn't we? And then these three terms, saturated, unsaturated, and supersaturated. There was a demonstration we did along with that. Make sure you're familiar with those terms and how you can tell if a solution is saturated, unsaturated, or supersaturated. Let me give you a bit of a hint. Let's say I had a solution and I wasn't sure if it was saturated or not. And I put a crystal of that solute in that solution. And as that crystal fell to the bottom, it dissolved. Yeah, well, it must be an unsaturated solution then, don't you think? Because as that crystal falls to the bottom of the beaker, it dissolves. That means that my solvent has not yet dissolved as much solute as possible. What if when I dropped that crystal in my beaker, it sunk all the way down to the bottom and just stayed there, and it didn't dissolve no matter how much I stirred it? That's right, that must be a saturated solution because my solvent can't dissolve any more solute. And lastly, what if I took that crystal, placed it in my beaker, I wasn't sure whether the solution was saturated, unsaturated, or supersaturated, and as that crystal fell to the bottom, it grew and got bigger and bigger and bigger, and a large crystal formed. That's right, that would be a supersaturated solution. And recall the demonstration that we did to help you remember that. Okay? All right, how about this? Number 2, draw the Lewis structure for O2, oxygen gas, and ethanol, C2H5OH. Which of these would you expect to dissolve in water, and why? Okay, we can do that. Oxygen's Lewis structure is pretty simple. You probably have it memorized because we've drawn it so many times. Okay, there's O2. And now ethanol, well, that's a bit more complicated. We have 2 carbons bonded to each other. One of them has 3 hydrogens bonded to it. The other carbon would have 2 more hydrogens bonded to it. And then we'd have an oxygen and a hydrogen bonded to that other carbon. So that would be the Lewis structure for ethanol. I drew the O and the H sort of in a bent configuration because that's what its shape is there at the end. Okay, which of these solutes will water dissolve? Well, remember the simple solubility rule. Like dissolves like. So let's draw the Lewis structure for water and see which one of these molecules it's more like. So the water molecule H bonded to O, bonded to H. It's also a bent molecule. Hey, can't the water molecule H bond? And can't the ethanol molecule also H bond? It has hydrogen bonded directly to oxygen. They're pretty doggone like each other, aren't they? They're both bent here at this portion of the molecule, and they can both hydrogen bond. So I would expect ethanol to dissolve pretty darn well in water. And oxygen, not so well. Oxygen only has LDFs that hold those molecules together, and if they were not in the gaseous state. Okay. Along with vocabulary, we did a lot of calculations. This was probably the hardest part of the unit for you, for some of you. We did molarity, molality, mole fraction, and weight percent. So I want to do one problem that, well, actually incorporates all 4 of these units. And so, let's say I have 2.56 grams of malic acid, C4H6O5. And I place that in a half a liter of water. Now, water's density is 1 gram per milliliter, so a half of a liter is 500 milliliters, so that would weigh 500 grams. I want to calculate the molarity, the molality, the mole fraction, and weight percent of the acid in the solution. Now we're going to assume that when I add these 2.56 grams of acid to my water, there's no change in the volume of the water. So it'd still be 0.5000 liters. So let's start with molarity. You guys should know the symbol for molarity is a capital letter M. And we need to have moles of solute on top and liters of the entire solution on the bottom. Now I give you grams of solute, 2.56 grams of C4H6O5. And obviously I need to convert that to moles. So let's put grams on the bottom and moles of C4H6O5 on top. Now the molecular weight of C4H6O5 is, let's find out, there's 4 carbons, each one weighs 12.01 grams per mole, and 6 hydrogens, each one weighs 1.01 grams per mole, and 5 oxygens, each one weighs 16.00 grams per mole. And so the molecular weight of that compound I get to be 134.10 grams per mole. So grams of the malic acid divide out, and now we need to find the molarity, so we need to divide by liters of solution. So remember we had a half liter, which is 0.5. It looks like I'm giving you 4 sig figs there, 0.000 liters. So I will have moles per liter as my unit, which is what I want for molarity. So let's see what that is. 2.56 divided by 134.10 divided by 0.5000. Looks like we have 3 sig figs, 0.0382 moles per liter. So a fairly dilute solution, which you would suspect. We only have 2.56 grams of that acid in an entire half liter of water. Okay, how about molality? So molality is symbolized by the small letter m, as you remember, and the numerator is the same, moles of solute on top, and we're going to divide by kilograms of just the solvent. Now in this case, my solvent's water. Okay, so we're going to start out the same way, 2.56 grams of C4H6O5. We want to hop out of grams and get into moles of C4H6O5. 1 mole has a molecular weight of 134.10 grams. So grams of malic acid are gone, and we need to divide by kilograms of water. Now this time it's pretty simple. We have 0.5000 kilograms. That's the same as 500 grams, isn't it? So in this particular case, my molality is the same as the molarity, which is 0.0382 molal. Now that's coincidental because my solvent mass is not always the same as the volume of the solution, but in this case it is. So keep that in mind. Molarity and molality are not necessarily the same. Just this particular problem, I made it that way for you. Okay, mole fraction. I want the mole fraction of the acid. So I want moles of acid on top, C4H6O5, divided by the total moles of my solute and my water. So this is going to take a little bit of work. Remember, we have 2.56 grams of acid, and we're going to convert that to moles. Again, that's right. So 134.10 grams per mole. That gives me, let's plug it in here, 2.56 divided by 134.10, 0.0191 moles of acid. Okay, and we have 500 grams of water. So we need to go from grams to moles of water. And water, as you recall, has a molecular weight of 18.02 grams per mole. So that's going to give us, let's see, 500.0 divided by 18.02. Boy, 27.75 moles of water. Now, we want the mole fraction of just the acid. So to do that, we are going to take the moles of acid 0.0191 moles of acid and divide it by the total moles, which would be the sum of the two. 0.0191 plus 27.75. And we're going to leave that as a fraction. So 0.0191 divided by, I'm going to use my parentheses key here, 0.0191 plus 27.75, and I'll close my parentheses. And I get a really tiny mole fraction. 6.88 times 10 to the negative fourth would be the mole fraction of my acid. And you would expect that because I barely have any acid as far as the number of moles are concerned compared to the total number of moles of my solution. And then finally weight percent. So weight percent would be the mass of the acid in grams divided by the total mass. And then we're going to multiply that by 100 to make it a percentage, kiddos. So let's see. The mass of my acid, remember, is 2.56 grams divided by my total, which is 2.56 and 500.0 grams times 100. So let's see, we get 2.56 divided by 2.56 plus 500. I use my parentheses key there. And I end up multiplying that answer by 100, and I get 0.509%. So 0.509% acid. So about 0.5% by weight is my acid. So hopefully you can see what I did there to fill in those squares. So my weight percent was 0.509%. My mole fraction, as you recall, was really tiny, 6.88 times 10 to the negative fourth. And my molality and molarity in this case were the same. Do you remember why? Yeah, because the volume of my solution in liters was the same as the mass of my solution, or solvent, excuse me, in kilograms. And the last thing that we need to review for this test is the last section that we covered, and that's solubility rules and ionic and net ionic equations. So review page 122 of your notes. Please have your solubility rules memorized for the test. This is a big portion of the exam. Now the best way to learn these is by practice, and I've tried to give you lots of practice in class. Let's try a few more, okay? All right. So let's write the molecular ionic and net ionic equation for silver nitrate reacting with calcium chloride. Let's write the ions down here to help me write the formulas. Isn't silver Ag plus and nitrate is -1? Calcium's +2 and chloride is -1. That takes us back a long time, doesn't it? Alrighty, so the molecular would be AgNO3AQ. All nitrates are soluble, no exceptions, and CaCl2AQ. All chlorides are soluble except for silver, mercury, and lead, so that's an AQ. Double replacement, folks. So silver will get together with chloride, AgCl, 1 plus and 1 negative, and calcium will get together with nitrate, CaNO3 Calcium's 2 plus, nitrate's 1 negative. Now, according to our solubility rules, CaNO3 is soluble. All nitrates are soluble. But AgCl is a solid. That's right, chlorides are soluble except for silver, mercury, and lead chloride. So that's a solid. We'll balance this by putting a 2 in front of AgNO3 and a 2 in front of AgCl. Okay, now let's do the ionic equation. Let's change colors so we can see the difference here in our notes. Ionically, silver nitrate dissociates into silver and nitrate ions, and since there's a 2 in front of that, we have 2 Ag pluses surrounded by water and 2 nitrates surrounded by water with 2 AgNO3s. Calcium chloride dissociates into calcium ions and 2 chloride ions, both surrounded by water. Now AgCl, we do not dissociate. It's a solid, kiddos, so water does not pull it apart. And the calcium nitrate we do, it's AQ, so calcium ions are surrounded by water, and we have two nitrates that are surrounded by water as well. So that is our ionic equation. Next up, we'll cancel out our spectators, and the spectators are the things that are identical on both sides of the equation. So these Ca2 pluses are the same, and these two nitrates are the same. And whatever's left is my net ionic. So let's write the net ionic. We have two Ag pluses, AQ, and two Cl negatives, AQ, react to form two AgCl solid. And if you wanted to reduce that to 1 to 1 to 1, that's fine. Feel free to do that. Okay, so make sure you can write molecular, ionic, and net ionic equations for your test. Let's do another one. Sodium sulfate and barium chloride. Sodium is Na+, sulfate, SO4 2 negative. Barium is 2+, and chlorides are 1 negative. So the molecular would be Na2, SO4, AQ. All sodium compounds are soluble, no exceptions. And barium chloride would be BaCl2. Barium's 2+, chloride's only 1 negative. And all chlorides except for silver, mercury, and lead are soluble, so barium chloride is soluble. Double replacement, sodium's going to get together with chloride, so NaCl, and all sodium compounds are soluble. And barium's going to get together with sulfate. Ba2+ and SO4 2 negative form BaSO4, and that's a solid. Now the sulfate rule is one that kids have a hard time memorizing. Sulfates are soluble, except for silver, mercury, lead, calcium, strontium, and our friend here, barium. So barium sulfate's a solid. Put a 2 here to balance that equation. All right, now notice I didn't do the net ionic here. We can jump right to the ionic pretty easily. And the way that we do that is we write down the solid on the right-hand side of the arrow. BaSO4 solid. And then the ions that make it up on the left-hand side. Ba2+ and SO4 2 negative. And so that would be the net ionic equation for that reaction. Okay? One more thing, electrolytes. Make sure you guys remember what electrolytes are. I believe that was the 10th video in the solution series, and we did a conductivity demonstration. And remember, electrolytes conduct electricity either in their molten state or when they're dissolved in water. And so, to find out if they're an electrolyte, do you remember what needs to be present? That's right, mobile ions. So it needs to be an ionic compound that when it's melted, the ions can flow past one another, or if it dissolves in water, the ions can flow past one another. So long as mobile ions are present, it's going to be an electrolyte. So take a look at these 4. Which of those would be an electrolyte? Hint, there are 2 of them that are. Take a second and decide. All right, welcome back. Carbon tetrachloride. Are there any ions there? Nope, that's a nonmetal to a nonmetal. That's a covalent or molecular compound. It is not an electrolyte. Sodium sulfate or phosphate? Yeah, that's made up of sodium ions and phosphate ions. And it dissolves in water really well. So this is an electrolyte. It definitely is. Gold. How about if I put a chunk of gold in water? Yeah, it's not an ion here. Here it's neutral. So this is just a metal. The metal would conduct electricity, but when I place it in water, it certainly wouldn't dissociate to form ions. So gold would not be an electrolyte. And finally, magnesium nitrate. Well, that must be the other, because I did say that there were 2 that worked there, didn't I? So magnesium nitrate forms magnesium ions and nitrate ions. So this is definitely an electrolyte. It would definitely conduct electricity when dissolved in water or when it was melted. Okay? All right, folks, that wraps up our review on solutions. Study hard, folks. Good luck on the test tomorrow, and we'll see you soon. Bye-bye.